Hi, I am Nicola Budini, a graduate student at the University of Colorado in the Department of Atmospheric and Oceanic Sciences, working with Professor Julie Lundquist. My research focuses on wind and turbulence. Wind, that is right, we study wind. But what is wind?
Scientists define wind as the movement of air in Earth's atmosphere. But how do we measure this movement? Traditionally, wind speed is measured by anemometers, while wind direction is measured with wind vanes. Today, scientists also use instruments like radar and LiDAR to determine wind speed. These instruments send beams of radio or light waves that bounce off tiny particles moving along with the wind. Wind speed is measured in distance per time. Weather forecasters usually describe wind speed in miles per hour, while scientists use meters per second. But what causes this movement of air? Ultimately, energy from the sun drives the wind. The sun's energy heats the Earth unevenly. For example, the regions closest to the equator receive more direct solar radiation, making them warm. In contrast, near the poles, solar radiation hits the surface at an angle, distributing that energy over a larger area. So places that receive a lot of solar energy warm up and experience an increase in air pressure. Similarly, this balloon expands over warm water. Therefore, the difference in global air temperature causes differences in air pressure. Air is a fluid. It flows from high pressure to low pressure, striving for balance. To visualize this movement from high to low pressure, we can imagine two bottles filled with water that are connected with a small pipe. If one bottle has more fluid and therefore higher pressure, then fluid will try to move to the bottle with less fluid or lower pressure. Air will flow from high pressure to lower pressure, creating wind. The force that drives air from high to low pressure regions is called the pressure gradient force. But the pressure gradient force is only part of the picture. Because we live on a rotating planet, the wind experiences additional forces due to the Earth's rotation. When we look at winds from the perspective of a rotating Earth, we see a force that appears to affect the direction of the winds. This force is called the Coriolis Force. The closer an object is to the axis of the Earth's rotation, or the further it is from the equator, the stronger it experiences the Coriolis Force. Let's visualize this effect. Imagine that we launch a paper airplane from Ecuador towards the North Pole. The airplane travels in a straight line, but the Earth will keep rotating underneath. From a viewpoint on Earth, it looks like that the airplane turns to the right. We call this effect the Coriolis Force. Winds that experience both the pressure gradient force and the Coriolis effect flow along lines of constant pressure. This wind is referred to as the geostrophic wind. So why are some places on Earth windier than others? And why do many places on Earth have a prevailing wind direction? The global heat balance causes the prevailing large-scale wind patterns. For example, most of the continental United States lies in the zone of westerly winds, referred to as the westerlies. The majority of our weather is transported by these westerlies. At the global scale, these patterns are established because of the global heat balance. Additionally, local wind patterns are influenced by local terrain and different surfaces. The windiness of a place is determined by interactions between the surface, the shape of land masses, and the pressure gradient. Close to the Earth's surface, wind speed is strongly influenced by vegetation or other structures on the ground. For example, trees slow down the wind, and scientists call this drag. Buildings or topography, on the other hand, can either slow wind down or channel air to speed it up locally. Across the world, prevailing winds have local names. For example, the warm winds on the Front Range of the Rockies, from Alberta to Colorado to New Mexico, are called Chinook winds, or snow eater winds. Let's summarize. Prevailing wind patterns are driven on the global scale by the Earth's energy balance and at the local scale by varying heating of the surface. The local wind pattern is also shaped by the roughness of the surface and the daily cycle of heating and cooling. All of these factors, heating, pressure gradients, Coriolis, and turbulence, work together to influence the wind that affects your daily life and our electricity production.